from this equation, torque net equals I alpha, we learned that it's not always true. And that kind of hurt for me because, like, why is it always, like, only sometimes true, right? Why is it not always true? And we saw the example of, like, when a figure skater is spinning and she pulls her arm in, there's no net torque, but she angularly accelerates, she speeds up. So this equation clearly doesn't always hold true. But what's the reason? Like, why does this only work sometimes, right? We don't have a law of physics that only works sometimes, right? So today I'm going to show you why it only works sometimes, or at least kind of a proof with calculus of where this equation really comes from. And then we can see, sort of, hey, now that makes sense why it's not always true and why it's only sometimes true. So what we do know is always true is that angular momentum can be changed by a net torque. So we know that angular momentum is equal to the rotational inertia times the angular velocity, I omega. And we know, hey, if we want to change angular momentum, if we want to change this stuff, I omega, we need a net torque. So what we do is, okay, well, I know that the derivative with respect to time of angular momentum is equal to the net torque. So I'm going to differentiate on both sides, I omega. So if you're kind of confused by that, basically what I know is that, hey, when I graph angular momentum versus time, hey, the slope is a change in L over change in T. That's our net torque, right? Because if you think about change in angular momentum equals torque net times time, that's why I'm differentiating with respect to time. This just gets me the slope, L over T, which is net torque. So now I can actually just substitute net torque in here. And okay, you might be thinking, well, I can just do d over dt I times d over dt omega, right? Because we're multiplying these two things. But when you're multiplying two functions and you're trying to differentiate them, let me just get my eraser, you got to use the product rule, right? You got to use the calculus product rule. So what I'm going to do is I'm just going to say, well, hey, this is like, I don't know, f and then g, so f prime g plus fg prime. So I'm going to do the derivative with respect to time of the rotational inertia times just omega plus, I, right, this function, times the derivative with respect to the time of omega. Okay, so this is just product rule, and I just expanded that. But what I want to show you here is that, well, when our rotational inertia is constant, right, there's no change in like rotational inertia over time. Like there is no change. Like the derivative with respect to time is zero. So if I switched markers just because my other one was dying, as you can see, got progressively fainter. D over dt for a rotational inertia, that's just zero times omega. There's no change in rotational inertia. That's what it's saying, right? Because remember, if we graph rotational inertia versus time for people not in calculus or haven't learned it yet, if I were to do inertia versus time, the derivative with respect to time, that just means the slope. So if the slope is zero, hey, it's just a constant rotational inertia. Because the slope is zero. If it's not zero, then it's gonna get bigger over time or whatever. So then we have just I times d over dt times omega. So hey, d over dt times omega, or not times, but the derivative of omega with respect to time, that's just our angular acceleration, right? If we were to graph omega versus time, the slope is just angular acceleration. So I can just get rid of this entirely, right? 0 times omega is just 0, so torque net is going to equal, now we have I times d over dt omega alpha. Torque net equals I alpha. So this equation just comes from the fact that torque net changes angular momentum, but when our rotational inertia is constant, we just get left with I times d over dt omega. In other words, we don't really have to care about the change in I because there is no change in I. So we just, with calculus, we can figure out that yes, this equation is true. It's just a special case when our rotational inertia is not constant. And that's pretty nice because in a lot of cases, rotational inertia is constant, right? For like a wheel, or for like I don't know, a sphere rolling, right? The rotational inertia is always a constant because it can't change its radius or anything. It can't change its mass, so it can't change its mass distribution. Um, so, there you go. This is a really handy equation, but it's just a special case. If you really want the most general form of the torque net equation, there you go, right? But most people don't care about the change in I, and then if there is a change in I, hey, just use, and then this equation can probably give you as well that torque net is equal to wait, no, what is it equal to? It's equal to the change in this times the change in that. And then you can just solve for, the change in L is equal to torque net times time. So yeah, there you go. That's the most general equation. So yeah, there you go. This was a short video. I just wanted to share it because I need to make more videos on this channel.